So this is all trivial to you. Just kidding. But it is true. I mean, if I'll remind you what the spectral radius of a matrix is, you'll say, "Holy shit, that's trivial." Okay. All right. So. So a few things about this last thing. I was sort of being a bit playful here. I mean, so somebody said, "Hey, you forgot the bar." I didn't forget the bar. Eta really is the steady state mean of C, you know. And so this is sort of weird right inequality because eventually it's sort of tight. But I'll explain this. Okay. So the point is to explain this. So there's and back to your sort of questions, I mean, really, in this sort of world, you know, for Markov chains, you know, that's typically what people mean. When they say Markov chain stable, they mean it's ergodic. And what do I mean by ergodic? Okay, ergodic has a different definition of every context you go to. There's a, you know, every physicist has a different idea, every statistician, every probabilist, every control person. Okay, but let's just call that the definition of ergodicity here. That this is just a memory that you forget the past eventually completely. As t goes to infinity, you don't remember where you started, you know, and there's a well-defined limit, you know, the probability of going from one state to another after t time steps. Eventually this looks like p of x prime, you know. So for this is equivalent to unichain and aperiodic All right, so it's equivalent to unichain and aperiodic if the state space is finite. You know, we've seen for the MM1Q is unichain, it's aperiodic. You can check that yourselves. But unless that factor rho is less than 1, it's not ergodic. Well, actually it is. I'm sorry. With this definition, it is. What's the limit for the Q where rho is bigger than 1? What do you think? Any intuition? So more people are coming to the Q than you could possibly serve them. The Q grows and grows and grows. What's that limit? Oh, no, remember, this is less than or equal to 1. What's the probability? So what's the probability that the Q length is 10? 0. So where P, so I have to put a caveat here, where pi is a probability. I better put that in. And otherwise transient Markov chains would be ergodic. Okay, so yeah, so I don't want this to be 0. But okay, so if the state space is finite, then saying it's unichain aperiodic is the same as saying they're equivalent. And you know, it's like you know, you're largely a control audience, so it's like I want to strip away the probabilistic part. And then just look at this through a linear algebra lens. So I will stay without proving. And I really struggled with this. And I was thinking, I mean, maybe I'll make you do it to the homework. Show that these are equivalent. I gave you hints. You know, if it's periodic, then there are eigenvalues on the unit circle. You know? And if it's not unit chain, if there's two different sets that are absorbing, if I start in this set, I stay there forever. I stay here, I stay there forever. You can show that there's two eigenvalues at 1. That lambda 2 equals 1 as well. There's two absorbing sets. So I mean, you know, this could be proven by all of us, but it would take a while. So I'll just say exercise. And maybe I'll give you a guided homework assignment, or maybe we'll just do it based on faith. All right? Or maybe just take that as a definition. A Markov chain is called unit chain and aperiodic if one eigenvalue is at 1, only 1, and all the rest are strictly within the unit circle. Let's take that as a definition. Because it is equivalent to this. It's a perfectly valid definition. All right. All right, and now I bring out the big guns. I talk about the spectral radius of Markov of matrices. All right. So how do we apply this? So let's see. And I mean. Of course, in both of these, I'm saying that the state space is finite. I mean, I'm saying there are D states. So P is a D by D matrix. All right. So how would I apply this? Well, okay, and well, I mean, you all see how this is related to this, right? That's P to the T, C. No. How's that? So we had, put this in the wrong place. I'm erasing my conclusion, conclusion 3, but that expectation is exactly the same as that. So that's the thing that we're interested in. And remember, my pi of C was a dot product. Okay, yes?
Which one you say it implies directly F out of the other statements A, B, C?
Well, the reason I snuck this in is because this implies this is like a one-liner.
Okay.
Okay. And this implies this is sort of messy, you know. At least I think so. So right? Maybe there's a quicker proof, you know.
Yeah.
I bet there is. I'll bet.
So E implies.
Yeah. I mean, it's really easy to show that if either one of these is violated, then this cannot hold. So one direction, you know, is easy, and yeah. But I think it's just a bit tedious. But the equivalence of these two could be done as an exercise, you know. And once we prove that this is equivalent to this, that implies this. So this implies this. We'll see is easy, and this implies this is easy. So, you know, sort of. So yeah. So maybe I'll make you all to go through the homework. We'll see. All right. But so how would I deal with this? So the trick is to prove that E implies F. Yeah, that is pretty satisfying. We'll see. E implies F is easy. I'm sure you all, if you thought about it long enough, would see that F implies D is easy. You know, and then that this implies this. Still, maybe it'll be a bit hard. I don't know. You could do it. But anyway, the proof that E implies F. So you change the problem a little bit. So change the matrix. So what does F say? F says that the limit as t goes to infinity of p to the t is equal to a rank 1 matrix. There's sort of this tensor notation you'll see. But what I mean by that is pi, pi, pi. You know, either one of these. That is just saying that this matrix, you know, it's row column. This column is a number that doesn't depend on the row. So all the rows are the same. Okay? So all F says is that p to the t converges to a rank 1 matrix. It's rank 1 because all of the rows are the same. All right? And 1 is a right eigenvector. And pi is a left eigenvector. All right? All right. So to apply this sort of spectral theory that 3 or 4 of you know, what you do is you annihilate this nasty, unstable eigenvalue. Okay. These guys are all less than 1, which for a discrete time systems theory person, that means it's a stable matrix. But it's got this annoying, what people call a marginally stable eigenvalue. You know? So kill it off. Sorry for the annoying notation. You know, I say I'm trying to save chalk, then why am I putting that huge cross with a circle? It's just, you know, again, I could just write 1 pi. A column vector times a row vector is a matrix. Column, row, matrix. And this ugly symbol is just to emphasize that's what I'm doing. All right? So what do you think p tilde squared is? See, the fact that these are left and right eigenvectors is useful. And what happens is all the cross terms cancel. And what you find is, I'm not going to do the algebra, you do it. You can prove by induction that if you take p tilde, it's a matrix, and you raise it to the nth power, you just get p to the n minus 1 cross pi. You know, it's this nice trick just to annihilate that eigenspace corresponding to 1. So I can just kill all this. We don't need it. Okay, so this is not a Markov chain trick. This is a trick in linear systems theory to annihilate a subspace. I mean, note that 1 is still an eigenvector. So by 1, I mean a vector of 1s. P1 equals 1. And what do you think this is? So pi is a row vector. 1 is a column vector. Pi of 1 equals 1. You know? So this is actually equal to P1 minus 1 equals 0. So 1 remains an eigenvector, but instead of an eigenvalue of 1, we've thrown it to 0. And the same thing with pi. Pi tilde. Okay, again. I mean, again, when I say 1 cross pi, I just mean this matrix. Forget about countable state spaces. Let's stick to a finite state space. Pi, 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 pi. And so I hit that by 1. I get pi of 1, pi of 1, pi of 1, pi of 1. That's 1, 1, 1, 1, 1. All right? Yep, okay. And the same thing here. Pi p equals pi. And then pi 1, I just am summing the entries of pi. That's 1. So pi 1 is 1 times pi. So pi remains an eigenvector, left eigenvector, but now the eigenvalue is 0 instead of 1. So I've just deleted that ugly guy. And so this is a lovely fact. And now we find that we can play around with spectral theory. So okay, you all said you knew what this meant. No, 3 or 4 of you did. Let's use this. Yep.
Why is that 0? Why is pi?
Oh, pi's invariant. Pi, when I say pi, I'm always going to mean the steady state distribution. It will never be 3.14159.
I'm sorry. I meant p times the 1 row vector.
No, p1. So remember what I mean. So first, when I say 1, I just mean 1, right? And remember when I say pv, you know, at x, that's equal to summation over x prime of px to x prime times v of x prime. You know? So if v doesn't depend on x prime, then I'm just summing over x prime, and that's 1. You know, p for every x, this defines a probability mass function. You know, for every x, this is a distribution on the state space. You know. You know, this is a probability of going to x prime. If I sum over all x primes, that's a probability of going from x to somewhere. So that's 1. Okay? All right. So what's the spectral radius of a matrix? Remember it's... Yeah. Yeah, you got it. I heard you. That's right. Let's call it rho of A. The spectral radius, let's call it rho of A. It's just what you said. It's the maximum over, you know, of absolute value of lambda 1, absolute value of lambda d. I know, me too. So, I know. So the spectral radius of a matrix is just the maximum of the eigenvalues, and so it's just what you said. It's, you know, visually. I should not have erased that. I'll put it back. Yeah, so geometrically, this is the case where 1, 2, 3, 4, 5, 6. This example, d equals 6. The complex conjugate symmetry makes you assume that A has real entries, which I'm going to assume. Okay, the complex conjugate symmetry is because A is a real value matrix. And yeah, again, in this example, d equals 6. All right, and right there is the biggest one. And we're not going to apply this with p, but p tilde. Yeah. So for so what we've done is we had that top eigenvalue that was 1. Lambda 1 was 1. But we killed it, and we made it 0. Because we wiped out that eigenspace. We kept it as an eigenspace, but we made it, we made the eigenvalue 0 now instead of 1. Okay? Yeah? All right, cool. And so we know that then the spectral radius is less than 1. And I can kill all this stuff. So here's the thing that everyone should know. If you don't know this, you should know this. That whenever you have a norm in RD, I mean, take the Euclidean norm, the distance, your Euclidean distance, that always induces a norm on matrices. Okay? That's called the induced operator norm, or induced matrix norm. And it's defined so that the norm of A times X is less than or equal to the norm of A times the norm of X for all X. Okay. The reason that people use these induced operator norms is because you get this nice bound. All right. And then and from this you get this wonderful result that what's the result again? I've got it in my notes. Somebody else tell me. It's a one-liner, and I just don't want to try to do it open loop. So, and I bought a cheat sheet somewhere. Let me go open loop, and let's see what happens. So, I take an eigenvector-eigenvalue pair for A. It's also V is also an eigenvector for a to the n. Okay, and how come I'm having trouble with this? Anyway, so so what you get is that the lambda to the n times the norm of V is equal to the norm of a to the n times V. And again, this is just a Euclidean norm. And then I use my inequality here. And then I can cancel things out. And that gives me a bound in one direction. It says for any eigenvalue lambda for A, that is upper bounded by the norm of a to the n for all n. And so I shouldn't have put a box around that. I should have taken the max over lambda here and said that that a to the n is greater than or equal to the spectral radius of A. So I'll put 2 boxes around that. To the 1 over n. Thank you, sir. There's a 1 over n missing here. Thank you. All right. So if the spectral radius is 1 or larger, there's no hope. This just gives us one condition. So we're in the other situation where we have this is less than 1. So we have a lower bound that's sort of vacuous. All right. So that's the negative result. It means that if the spectral radius is greater or equal to 1, then a to the n cannot go to 0. Yeah. But here we have the opposite situation. Rho of A is less than 1, and it turns out that implies that a to the n does go to 0. So that gives you just one part of a big theorem. If the spectral radius of A is greater than 1, then a to the n goes to infinity. And if you actually look at this, put this back like that again, that's bigger than 1. So this goes to infinity geometrically fast, right? And if it's less than 1, I'll put an if and only if there. No. And if conversely, if it's strictly less than 1, so when I say geometrically fast, how fast do you think I mean? For those of you who've taken state space control. What? Yeah, well, yeah, oh yeah. I mean geometric like something less than 1 to the nth power. Yeah, but like what is that constant? You know?
The biggest of the non-1 eigenvalues.
Yeah. Well, no, they're not 1 anymore, right? I mean, my A, I've taken A to be P tilde now, so I'm assuming the spectral radius is less than 1.
So the largest one.
Yeah, it's almost true. You know, it's almost true. So you're almost right. So you can refine this, and it is true that the limit as n goes to infinity of 1 over n times the logarithm of a to the n. I mean, excuse me, guys. A to the n norm.
Yeah.
Okay.
Same one above it.
Yeah, sorry. Sorry. God, that would be really vacuous. This is true. So in this weak sense, it's true. So this is going to zero geometrically fast. So it's like a constant to the nth power, with a constant less than 1. This is consistent with what you said. All right. But remember when there were repeated eigenvalues? What goes wrong? For those of you that had state space control? You can't diagonalize. Well, it's not the rank condition. It's the fact that you can't diagonalize means you have to do some really ugly nonsense that comes in. The Jordan canonical form. So what happens is, in reality, this is like rho to the n, but times like n to the k, or something. You know, depends on how many repeated eigenvalues you have. So if you can diagonalize, then it's precisely that. You know, if you can diagonalize, then you get a very clean answer. But anyway, the proof. Okay, so 1 I proved, all open loop, modulo typos, I got that. So if the spectral radius is bigger than 1, you know, this blows up. 2 is the Jordan canonical form.
So you go through and you try to diagonalize the matrix, but you can't quite do it. But J is almost diagonal. It's got a bunch of, go back and look it up. If you have, don't worry about it if you haven't seen this, but you have a bunch of zeros here, you have eigenvalues in the diagonal, and then ones and zeros just off of that. And when you raise this to a power, you see that it goes to 0. It's just exactly like that. So it's just, you have to, there's some muscle there. So now what, you have to have some machinery somewhere to prove this result. And the machinery with this kind of proof is using this Jordan decomposition. All right. The fact that, yeah, I mean, if all the eigenvalues are distinct, J is diagonal. Otherwise it's not. And the nice thing is that with this decomposition, this goes to 0 if and only if that goes to 0. QED. All right, so you proved an ergodic theorem. And you won't see that proof in any book that I know of. It's just, it's tailored for this audience because you're more of a control audience. Yeah. So, okay. Questions? Yeah? I mean, you know, I guess it's not obvious I proved an ergodic theorem. I mean, reminder, remember we're applying this with A equals P tilde. All right. And so now we know that P to the tilde to the n does go to 0 as n goes to infinity. But we already said that that's equal to P to the n minus 1 cross pi. You know. And we even know that goes to a geometric rate. We have this nice result here. We know all about it. And this going to 0, just evaluated x and x prime. So when I take this matrix and I evaluate it at x prime's entry, think, you know, x is an integer, you know, the 2, 5 entry, whatever. I take p at its entries minus this at its entries. And remember, this is a matrix with all the rows being the same. So it's just pi of x prime. You know, so just by reinterpreting what we had, saying this goes to 0 is the same as the ergodic theorem. All right. Okay. Now, if I was going to really present conclusion 3, you'd have to take a much bigger course, you know. But you know, you can get really precise results. I mean, you can improve this a lot. And I won't. I mean, just, there are, I mean, yeah.
Does that make sense? How do we extend like this intuition to the non-finite, like P is not a matrix, I want to see it as that expectation operator and still have the same feelings?
It's all, yeah, that's the most amazing thing. I mean,
it's not quite there yet.
Oh man, I mean, you're gonna, I'll do it. So it's really kind of fun. I mean, who here likes functional analysis? I mean, but like the MM1Q. I could work out all the eigenfunctions for you. It's reversible. It means its eigenvalues are real.
We know there's one at 1, right? So, you know, looking at poles, you know, so, you know, PV equals lambda V. Want to hear something sad? The entire, every single real number between 0 and 1 is an eigenvalue. So the spectral radius is 1. The spectral radius of P tilde appears to be 1. It seems like all this hard work goes out the window. Okay. The difference is that when you go to a countable state space, you can't just talk about a vector. You have to have a norm. You know? So if I restrict, if I consider PV equals lambda V, but restrict V to be in some function space, I'll call it H, say. I don't like H, B. So put some constraints in. For example, the favorite one is L2. Everyone loves this. There's lots of good reasons to like that. That's one example. I'll break that. Forget the P there. Delete the P. It looks too much like an LP space. Forget that P. So if I define this to be a norm, and I look at the space of all vectors, such that this is finite, then I wish I had my colored chalk. Then suddenly I get a spectral gap. Everything changes. You end up with an interval here, a gap, and then always we have that eigenvalue at 1. Because you know we can always plug in 1 and get P1 equals lambda equals 1. So I have a whole book on this topic, and we argue that this, even though this is the favorite thing used by mathematicians, it sucks for a lot of applications. And so we looked at alternative, you know, spaces of, you know, function spaces. I mean, I'm thinking of V as a function, right? So alternative function spaces, you get a much crisper theory if you're not settled by this particular space. And so yeah, so that having a spectral gap, all the theory then applies. I can talk about the induced operator norm. I can talk about everything. You know, I can knock out that and get a spectral radius which is less than 1. There's no Jordan form, but there are substitutes for that. You know. So I didn't need the Jordan form to prove this result. I only used it because that's something that state space, you know, control people and communications people should know. Yeah. Well, there are. Yeah, it turns out that for the MM1Q, it has a continuous spectrum. So you've got every single, there's an interval here. I think it's like the square root of rho or something. There's every single real number between, I think, minus square root of rho and square root of rho is an eigenvalue. And you can find, it's easy to find the eigenvectors. It's a difference of exponentials or something. You know, and yeah, so it's, yeah. And that's what happens is that as lambda gets closer to 1, these functions blow up faster and faster until a threshold here, I guess it's open, where this is no longer finite. You know. All right. So yeah, that's something, I mean, I'd love to talk more about that. And it's so cool, I mean, it's very new work, conditions under which there's actually discrete spectrum. So the MM1Q has a continuous spectrum, and under certain Lyapunov conditions, which are much stronger than what I've shown you, there's actually, in any tiny ball around the origin, you look at the complement, there's only a finite number of eigenvalues. And that has a lot of value for approximation. So if you want to approximate a complex Markov chain by a finite state space Markov chain, having a finite discrete spectrum is really valuable for this one person who likes functional analysis. Yeah. So yeah. So it is useful to think this way, even though it's not a typical way to look at these problems. I know I have parting words. Wow. Crazy. I can't believe what I thought I might be talking about today. There's about 4 more hours of material here if you'd like to. So, yeah, so I don't know how to do this exactly. So there's so many things to say. So we have this notion of ergodicity done. Remember when we talked about the stability theory with ODEs, we had sufficient conditions and then converse theorems. You know, so we had a Lyapunov condition, and we said, if the system's stable, then a Lyapunov function exists. We don't need all that, but we do need representations of these things very much. So that's what, I'll give you examples next time, but also some more theory. When I say I want to solve pH equals H minus C plus eta, we need representations of this just to get some insight. You know, so we'll know like what we're looking for. And so I'll spend probably most of the next lecture on representations. I've got lecture notes for that I have passed out in previous courses, but they're based on appendix of my networks book, and they're way too much. So I'm going to edit them and take the really complex stuff and put in an appendix, so you won't have to pick out the important parts, because I'm not going to go into that much depth. But we want representations for H. We need that to get algorithms. You'll see, we really do. So that'll be next time. Yep.
Is there any significance to you changing your Lyapunov function notation from V to H?
Oh, yeah. I mean, so when I talk about stability analysis, I'm going to use a V. So that's what I was calling like Poisson's inequality, you know. But when I'm talking about something crisp like this, equality, I'm using H just to be very distinctive, because this is very fragile. I want to compute exactly this dynamic programming equation, you know. And here I'm just trying to get a bound. Yeah. So this is Lyapunov theory, and here is like, you know, what do they call this? So like in math. Well, anyway, dynamic programming equations. Yeah. There's another term for it in potential theory. That's right. Yeah. that's what this would come about. All right. So it's a good time to quit. It's definitely don't want to start a new topic. Any questions on the homework? Haven't started it, have you? I knew I should have made it due today. All right.